Welcome to the Explainer. Okay, let's just dive right in because today we're looking at a truly monumental shift in how we handle information. We're talking about the complete evolution of massive data storage and processing. Honestly, if you work with data at all, or even if you just generate it, which let's face it is literally all of us, understanding how the architecture behind the scenes has transformed over the last decade is absolutely vital. We aren't just going to look at where data lives either. We're exploring the whole shebang, the entire data pipeline. We'll track the journey from fundamental shifts in storage architecture all the way to those flexible NoSQL databases and the advanced machine learning algorithms that define modern analytics. Traditional systems had to step aside and make room for something completely new. And today, we're finding out exactly why. It all really starts with one very fundamental question. How do we store data when the data simply gets too big? To truly wrap our heads around this, we have to think about the big data Vs, specifically volume, velocity, and variety. You see, for a long time, the tech world had a pretty standard answer for storage. But when the big data boom hit, it wasn't just about file size anymore. It was about petabytes of information flowing in every single second, moving at unprecedented velocity, and arriving in a massive variety of completely unpredictable formats. The traditional systems we relied on, they just began to buckle under this immense pressure. They quite simply couldn't handle the scale or the speed. And that brings us to the core matchup of today's explainer. On one side, we've got RDBMS, the Relational Database Management System. For decades, this was the absolute, undisputed king of data storage. But on the other side, we have Hadoop, which utilizes what's known as a node-based flat structure. But here's the thing. Hadoop isn't just a single tool. It's an incredibly powerful, sprawling ecosystem. Down at the foundation, you have HDFS, the Hadoop Distributed File System, which acts as the storage layer, making this flat structure possible. Then, sitting right on top of that, you have MapReduce and Yarn, pulling the strings as the processing and resource management engines. Getting a grip on the contrast between traditional RDBMS and this entirely new Hadoop ecosystem, that's your key to unlocking modern data analytics. Now, what's really fascinating here is the analogy of rigid versus fluid. With RDBMS, you are dealing with a system that demands structured data. It completely relies on consistent relationships. Think of it like a highly organized, extremely structured filing cabinet. It works beautifully, but only if every single piece of paper has a specific, predetermined folder it must go into. But Hadoop is built from the ground up for analytical big data processing. It operates way more like a massive, flexible, open warehouse. It doesn't require any consistent relationships between the data points at all. And this fluid paradigm actually paved the way for entirely new database architectures, specifically NoSQL databases like MongoDB and Cassandra. These NoSQL tools absolutely thrive in environments where data just refuses to fit into neat little interconnected tables, giving developers unprecedented flexibility. So Hadoop isn't just okay with unstructured data, it actively thrives on it, supporting a huge variety of real-time formats. We're talking XML, JSON, and your standard text-based flat files. Because in the wild, data is incredibly messy, right? It doesn't arrive perfectly formatted with a bow on top. But how do you actually make sense of all this messy data once it's just dumped into the system? Well, this is where data analysis translation layers come in. Tools within the ecosystem, like Hive and Pig, sit right on top of this unstructured data, and they allow data scientists to run complex queries almost as if they were using a traditional database. Then, visualization tools, think Jasper reports, can turn those queries into clear, actionable insights. You don't have to painstakingly clean the data before storing it anymore. You just ingest it as is and process it on the fly. It's a real game changer. Let's shift gears and look at the physical reality of these systems, because the architectural difference is pretty stark. RDBMS is doing a lot of heavy computing just to maintain those rigid, consistent relationships. So naturally, it requires high-end, extremely expensive, centralized processors. Hadoop takes the exact opposite approach. Taking full advantage of its flat structure, it runs on a Hadoop cluster made up of simple nodes. A single node really just needs a basic processor, a network card, and a few standard hard drives. So how do all these simple, scattered parts work together without a massive central brain? That is the absolute magic of Yarn, yet another resource negotiator. Yarn essentially acts as the operating system for the cluster, brilliantly assigning processing tasks across the network without ever needing that high-end centralized hardware. Let's talk about what that difference in hardware actually means for a business's bottom line. Prepare yourself for a bit of price tag shock here. Maintaining an RDBMS can cost anywhere from $10,000 to $14,000 per terabyte of storage. Let that scale up in your mind for just a second. If a Fortune 500 company needs to store just one single petabyte of data, which remember is 1,000 terabytes, they are staring down an incredibly painful $14 million bill just for the underlying storage hardware. When you're dealing with global, real-time data, that cost becomes a massive, suffocating barrier to scaling up your operations. It's just not sustainable. But by utilizing those cheap, simple nodes we just talked about, a Hadoop cluster slashes that price down to around $4,000 per terabyte. Yeah, you heard that right. You are dropping from up to 14 grand all the way down to 4 grand. A petabyte suddenly costs 4 million instead of 14 million. But the true impact of this isn't just about saving some cash on hard drives. It is all about what that saved capital unlocks. By slashing the fundamental cost of storage, organizations finally had the massive budgets they needed to invest in what actually drives the business forward, building out advanced analytics departments, hiring top-tier data scientists, and ultimately developing next-level predictive models. It sounds like the absolute perfect solution, doesn't it? You get incredible flexibility, you get real-time processing of incredibly messy data, and you get it all at a total fraction of the traditional cost. But is it cheaper, flat structure, flawless? Of course not. In the world of tech, every single solution introduces a new set of complications. You are fundamentally trading financial risk for architectural risk. When you move away from that single, expensive, highly fortified processor and start relying on a sprawling network of cheap, everyday machines, you introduce an entirely new paradigm of system vulnerability. Which brings us directly to a major hurdle: distributed computing challenges, hardware failure. You really have to understand the inherent statistical realities of this setup. In a distributed system, you are networking several off-the-shelf servers together to act as one massive machine. That means there is a very, very high possibility of hardware failure. I mean, it's just pure probability. If you have one extremely expensive, redundant machine, you have one point of failure. But if you wire together 10,000 cheap, simple nodes, it's not a matter of if a hard drive or a network card is going to fail today. It is a virtual guarantee that several of them will simply die. The creators of this ecosystem knew this. They knew they were trading reliable hardware for cheap hardware, which meant they needed a brilliant software solution to fix a physical hardware problem. Which leads us to this critical question. And when such a failure does happen, how does one retrieve the data? Well, the brilliance of this ecosystem lies in HDFS data replication. When you drop a file into Hadoop, the system automatically creates multiple copies and scatters them across different nodes in the cluster. If a machine literally catches fire, the system doesn't even blink. It seamlessly pulls the exact same data from a surviving node. Hardware failure is entirely expected and mathematically planned for. And once your massive, messy data is safely stored and cheaply processed, well, that's when the real magic begins. This architecture allows you to deploy advanced machine learning algorithms like regression analysis, K-means clustering, and decision trees to chew through that data and uncover patterns no human could ever possibly see. We've officially conquered the storage problem, but are we truly ready for the staggering insights these algorithms will uncover next?